Thank you, Erica. So I'll tell you about some recent work we're doing on essentially ways to help you figure out what kinds of data is more useful and hopefully get more out of your data, right? So hopefully that's interesting to everyone here. Um, so as Erica mentioned, I'm very fortunate to be the faculty director of our AI for Health initiative. So I think it's a really exciting area, right? This is really in the intersection of machine learning, digital health, genomics. So the approach that we're taking in our group is to really look at this health from across quite a wide range of physical scales, all the way from the smallest molecular scale to the largest sort of population level, right? So at the smallest molecular scale, for example, we've developed some of the first machine learning algorithms that improves the safety of genome editing, right? So it allows you to edit the human genome and tell you which are the safe places to edit and which locations are not so safe, right? So at the individual level, so we actually have a collaboration with Ewan's group where we developed AI technologies to take ultrasound videos and to diagnose and to measure and quantify various cardiac functions just from the ultrasound videos. I think this is really one of the first AI technologies that we'll try to push out for the cardiology space. So we're also very interested in, and also in collaboration with some of the companies here, looking at the larger scale data sets. Right? So for example, we're collaborating with Anthem and also with Virtusa, looking at data sets of maybe large medical records, claims data from populations. There's a lot of interesting natural language processing, machine learning, cost prediction problems involved. And we're also collaborating with Genentech, who's also an affiliate member of AI for Health, where we are helping them to essentially apply machine learning to optimize for clinical trials, right, especially for cancer trials. So we'll actually have a student in my group, Rishan Lu, who will talk about that particular project after lunch. So if you're interested in any of these, happy to chat more about it. So I think there's a lot of interesting space for collaboration between the kind of research we do at Stanford and some of the industry company interest. So these are working with very different types of data, right? But the common thread of this is that typically the data is actually quite noisy, and it's also very expensive for us to collect, right? So if you are like a researcher or engineer, you're getting data maybe from different hospitals, from different experiments. So a core sort of existential challenge you face is how do you figure out what kinds of data is really useful and what kind of data is just providing noise or adding junk to your signal, right? Or if you're on the company side, right, so maybe you have to make decisions about how much to invest in what data to collect or how much to pay to collect data from different companies, right? If you're a data vendor, so that you have to figure out how much the data is worth. And also even just from the regulatory side, there's actually been a lot of discussions recently about how do we figure out what kinds of personal data is really useful so that companies can quantify and can compensate individuals for the data that they provide, right? So there's been legislation in the US Senate and also specifically in the state of California about data dividends, whereby companies will compensate individuals for their data. So the technical challenge, right, so the machine learning challenge that underlies all of these questions is really to think about how do we figure out what kinds of data is really useful, right, in a given task, and how do we use that to try to basically get more out of this useful data. So I'll tell you about a couple of recent projects that we've done, right, to try to really quantify this and to put it into solid and develop some technologies to try to address these questions. Right, so this work is really led by a fantastic PhD student, Amir Atta, who's a PhD student here at Stanford. So just to take a step back, right, so here's the generic kinds of machine learning pipelines that I think many of you would face in your research, right? So you have some data, maybe data you're collecting maybe from different hospitals, from different patients, or from different locations, right? And you have some training algorithm, maybe some optimization techniques. Maybe you want to train your favorite neural networks, right, on that data. And you have a particular objective, right, for which you want to build this product for. Right. So for example, if you are kind of an insurance company, maybe your data would be medical claims, your algorithm would be sort of natural language processing, and your performance objective is maybe you want to improve your coding accuracy. Right. Or if you're working on the image space, your data would be images, your algorithm would be some sort of image recognition systems, right? And your outcome of interest could be your segmentation or detection accuracy. Right. So our goal is to say, okay, so regardless of what kinds of specific application you have, right, can we create some ways to quantify figure out what kinds of data is useful in each of those applications. So what do I mean by useful? Right, so the idea here, to be more concrete, is that, so let's say if your algorithm for this particular performance metric, actually achieves, let's say, 80% accuracy, right? So maybe that's doing pretty well. So you want to figure out, so here you have three example data points, right? So you want to figure out which of those type of data is actually contributing the most to this 80% accuracy, right? So you want to basically partition that 80% accuracy to each of your individual data points or to each of your individual sources of data and figure out who's actually contributing and who's not contributing, right? So if you can do that, then you can have better ways to allocate your resource, and also you have better ways to improve your model. I'll give you some examples of that. So how do we actually do this? How do we attribute the performance of a system back to the individual data that's used to train that system? So that's the key technical problem. So the idea that we propose to solve this problem is actually very much motivated by some ideas coming from economics. Right, so in economics, people have to basically solve the following problem, which is that imagine if all of us in this room, if we work together and we solve a puzzle and we get $100 of bonus. Right, so then how do we split up the $100 to each of you, right, so that you're happy with your share of the bonus and people don't complain? So it's a very core and challenging problem. So it turns out that it's amazing results, which is also recognized with the Nobel Prize in Economics, that there's only one unique way to split up that $100 bonus among each of you so that you're happy with your share of the bonus. Right? That's the idea called the Shapley value, which I will explain. So our contributions, in our work, we basically extended this idea of the Shapley value to setting of data. So instead of each of you now, imagine each of you actually come with your own data set. Right? So you have different people with your different data sets, and then the algorithm works on all of those data to achieve some performance. So the performance then is the bonus. Right? So now we can actually split up that bonus among each of your data points so that your data actually gets its fair credit for its contribution. So we're proposing this idea that we're calling the data Shapley value. Okay, so how does this work? All right, so I'll just show you how this works through a set of sort of simple scenarios and cartoons. Right? And all of this can be quantified more precisely mathematically. So the idea here is that imagine if I just have these 3 data points and you train a model. Right? So maybe the simplest thing I can do if I'm trying to figure out what is the contribution of this star point in the middle is that I would just take that star out and see how does that actually change my model's performance. Right? So I just take the star out and put the rest of the data points through my pipeline and see how does the performance change. Okay? So that's what people typically do, right? When they try to quantify the value of the data. That's called the leave one out kind of estimates. So it turns out that that's actually not a very good idea by itself. Right? So instead, what we do is that we create a bunch of different scenarios where each scenario corresponds to a hypothetical setting where you have a different random subset of your data. Right? So each of the scenarios, think of that as sort of like a counterfactual. And on each scenario, I'm going to remove this point star and see how does that change the algorithm's performance in that scenario. Right? And it will have different effects in different settings. And then what we do is essentially we can aggregate across those different randomly generated scenarios, and there's a unique way to aggregate it that gives us what we're calling this data Shapley value. Right? So that's our idea for doing this. So I'm happy to go into details, but here's essentially how you can do this mathematically. But it's basically capturing the same idea I showed you in slides. Okay, so I want to show you a couple of applications of this in the healthcare setting, but I think this can be broadly applied to essentially any kinds of, to much more general settings. If you're working with finance, consumer space, you can also try to apply these kinds of approaches. So the first setting is, can we actually use this data value to figure out what kinds of data is actually hurting my model, right? What kinds of data is really, really noisy? So one setting that's actually is very prevalent is actually in sort of medical imaging. Right, so many of you here have probably heard about, there's a lot of recent interest in developing AI systems, for example, to do automatic diagnosis from skin lesions, from skin images. Right, so it's really exciting, but the data that's actually used to train those skin recognition algorithms are actually extremely noisy. Right? So what they do actually is to go on Google Image, type in as queries the names of different skin diseases to scrape large data sets of Google Image. So the training data used to train that, is literally some examples shown here on the left, right? So extremely noisy data. When we actually apply that in clinical settings, the performance can drop a lot, right? It can make mistakes on the clinical examples. So now with this data Shapley value, we actually have a number for each of my training image that says how much did this image contribute to the success or failure on application, right? And in particular, there's a lot of images that have very low or negative value, right? So they're actually hurting my model because they're too noisy, right? So I can just throw those out. And then I can only maybe just focus only on the subset of my data that have known to have the high Shapley value, right? So here are some examples of those. And if I just simply retrain my algorithm only on the high Shapley value data, right? So the performance actually improves by double digits, right? Because now it's actually working on a cleaner data set. The other way we can look at this is that we can look at the data points that have low Shapley value, the negative Shapley value ones, right? So I'm telling you that they're hurting your model, so how do we check that? So we can actually go back to check them individually, see are those actually misannotations or mislabels. Right, so it turns out that here what the blue curve shows that if you actually look at the data points that have the lowest Shapley value, those are exactly the data points that have mislabels and misannotations. Right, so they're just introducing noise in the system that are hurting the model. So the second example of this, right, is an application to the UK Biobank. So the UK Biobank is an amazing data set. It's actually one of the largest and most useful data resources in the biomedical community. Right? It has 500,000 people in the UK with their genetics data, medical records, so it's a really fantastic data resource. So it turns out in the UK Biobank, so the data actually come from, these 500,000 people actually come from these 22 locations, right? The 22 cities in the UK. So the bars here actually corresponds to how many participants are from each of those two cities. And now we can actually compute what is the quality, the value of the data that are generated by each of those locations. And this is actually extremely surprising to us, right? So here we're just showing you blue what the Shapley value corresponds to each of those 22 locations. And the thing that's really surprising to us is just how heterogeneous the values are. Right? So in particular, you have a few locations, including 15, which is Nottingham, where the data will actually have negative Shapley value, right? Which, as we saw before, right, it actually means that the data is actively hurting the performance of my model. So here we're looking at taking off this data to train for like a lung cancer kind of diagnostic algorithms, and we've done this for other disease diagnosis tools. So what we can do now is to actually just also remove the individuals that have low or negative Shapley value, right? So that's what the plot on the left shows, right? So actually removing those individuals, the model's performance gets better, right? So that's great. The other way we can use this is to basically do resource allocation. So now that I know which individuals, what kinds of individuals have high value, right? So can we actually recruit more individuals like those ones? Right? So we can basically simulate this kind of recruitment procedures and show that if you actually recruit individuals by high Shapley value, you can actually improve your model much more effectively than if you just recruit from the general population. Right? So that really helps with the active learning. So just to summarize, I think sort of, if you really want to get more out of your data, you have to figure out what kinds of data is useful and what kind of data is hurting your model. Right? And we think of this data Shapley approach as one very general and principled approach, right, to quantify the value of the data, and we have developed efficient algorithms to quantify this data value. So a very recent kinds of development that we've done on top of this, right, is to really push this forward to figure out this concept we're proposing called Neuron Shapley, which in addition to saying which kind of data is really useful, we can also now quantify what specific part of your model is really useful. Right, just to give you a quick example of this, right, so if I actually train a deep neural network for image recognition, right, so typically this network would have on the orders of tens of thousands of artificial neurons, right, in different layers. So here's just a standard network for image recognition. So it turns out that we can actually apply very similar technologies as data Shapley, right? We can extend that into what we're calling Neuron Shapley, where we actually compute how much did each individual neuron contribute to the performance of your model, right? Each of these 20,000 artificial neurons in my deep network. So here, the extremely surprising, interesting fact is that there's only 5 to 10 neurons that are out of the 20,000 that are really useful, right? That we can identify by the Neuron Shapley. The way we know this is that if I remove the most useful neurons, right? That's the blue curve. If I just remove 5 of them, the entire performance of this neural network has collapsed, right? Whereas the red line corresponds to if I remove random neurons from my network. Okay, so basically there are only 5 neurons, right, in this whole network that are really necessary for your prediction. Right? So here are the predictions just for illustrations to predict volcano images. Right? So you can ask, okay, so what are these 5 neurons? So it turns out that the most important neuron, you know, it sits on here. I'm showing you like the location for that neuron. It sits on the 6th layer, on the 2nd branch. But what that neuron is really doing is really look for cloud-like shapes. Right? So it turns out that in this whole big network, there's only one neuron that's looking for clouds, and that ends up being extremely critical for predicting volcanoes. And there's actually very little redundancy in this network. Okay, the second most important neuron is actually, we can visualize what it's doing. It's also sitting somewhere in the middle of the network, and it's basically looking for sort of green mountains. Right? And there's only one neuron in this whole network that's looking for green mountains. And if that neuron is not there, then you cannot actually predict volcanoes. Right? So this actually shows you that there's only a few neurons that are really crucial. Right? The flip side is also interesting. We can say, okay, so you have all these other 20,000 neurons. What are they doing? Right? Can we just get rid of them? So we can do the opposite approach. We take the ones that have the least value, start to prune them away. Right? So that's the blue curve. So basically, it shows that if I actually start to throw away neurons, the performance of my model is actually getting better. Right? Because I'm removing the ones that are hurting my model, and I can actually throw away about 15,000 of them while still having a better performance of my model than if I had the full model. Right, so this is interesting from a couple of perspectives. Right? So scientifically, it shows that these deep networks are actually extremely, there's only a few parts that are really crucial. Right? It also allows me, if you're interested in trying to compress your models, right? Now you can just prune away most of your neurons and actually get better performance. And also going back to this idea of resource allocation, right? So now you understand there are only a few neurons that are really critical. Now you can actually put more resources to test, to robustify, validate those neurons. Okay, so this is idea of, I think they're quite closely related in that data Shapley is to figure out which data points are important. Neuron Shapley tells you what component of your machine learning model itself is really important. Okay, so and we have also done a lot of work in really trying to make all of these tools, deep learning tools, publicly accessible, right? So many of you know about GitHub, which is a code repository. We've also recently created Gradio Hub, which is like GitHub, but we can actually run the code in real time on your browser. Right? So all the codes are immediately runnable on the browser without any downloads or setups. So I think that is a tool to make all these deep learning tools much more easily accessible. Okay, so I'll just wrap up here to thank our company partners, Anthem, Genentech, Virtusa, and also my students and other people who have been really supporting and our collaborators on these projects.
With the Shapley value that's coming from economics, maybe I'd like to know if I'm inferring this incorrectly, but would a consequence of your scholarship or research here be that individual lay users, contributors of data, could be remunerated for the quality of their data as it contributes to a model? Are you not saying that explicitly, or is that a false or real implication?
So I think that's certainly one interesting potential application of this approach. Right? There's also been a lot of policy discussions about compensating individuals. So we think of the data Shapley value potentially one approach to start doing that. I don't think it's quite all the way there yet. I think there are some other technical challenges and also ethical challenges we need to discuss. But I think there's certainly one way to at least have a well-defined way to define what's the value of the data.
So another question. So when you were removing all those neurons, like thousands and thousands of them, how would you then connect the network in their absence? Right.
Yeah, so there's a few ways we can do that technically, but we'll just do the simplest way where if I remove neuron, I essentially just blank it out, right? So there's no signals propagating forward from that neuron.
So a quick question. You were talking about, greedily adding points that you know that you have a high Shapley value, right? But that assumes that you know the label of the data. So have you thought about a modification of this kind of the active learning kind of thinking where you can estimate the potential Shapley value given either one of the labels that you need? Or
that's right. Yeah, so that's a great question. So we are actively working on doing the active learning aspect of this. Right, so I showed you actually this example from the UK Biobank. So we can actually do that example of the UK Biobank where we simulate recruitment of new individuals, or we only know some features or some summary information about an individual without knowing their labels. Right, so basically from that, we can actually infer enough information about their values so we can figure out what are the more useful kinds of data to collect.